faster. The reason is that the things are very mathematical, and still we have left many things to finish regarding application-oriented things. Okay, but I will be leaving few slides for you to be handled with, because these things are related to Fourier transform properties and completely mathematical. If we have a real signal, then what will be the properties of Fourier transform? And if we have an imaginary signal, what will be the Fourier transform? Please look at table 3.4. As you know that your Fourier transform as well as Fourier constants that we have determined for the case of Fourier series, all are complex quantities. Then those complex quantities will have a real part as well as an imaginary part. If we have a real signal, you see that your Fourier transform will be conjugate symmetric, even symmetric, but your imaginary signal, it will be conjugate odd symmetric. And same is true for Fourier constants. And this is also true for continuous time as well as for your discrete time. Okay, probably I have shared PDF. Let me share. The PowerPoint. Where is the PowerPoint? Let me see. So I will be skipping few things. Again, it is problem. Gradually getting sick in taking online classes. So we will be skipping few properties. They are very mathematical, and you try to look at it. But the important ones will be discussed in this class that we need for our future applications. For example, the convolution properties of our signal. We have two types of signal, you know, periodic and aperiodic. For convolution properties for periodic signal, we will take periodic convolution that we will discuss. But this is particularly beneficial for aperiodic type signal. And probably this property is with you when we have been introduced with Laplace transform. That you see that if we have our two signals in time domain, those signals are say HT and XT. If we have two signals HT and XT in time domain, then if we want to find YT, that is the convolution of HT and YT, this equation we use to determine the zero state response of a linear time invariant system. When your HT is your impulse response, XT is your input. Then if we take Fourier transform, then this transform equation will be something like this, okay? That means the transform equation become the multiplication, where your xj omega is the Fourier transform of xt, and hj omega is the Fourier transform of ht. So if the input Fourier transform and the frequency response are known to us, then we can multiply them together to find the output transform. Then we take the inverse just to find the time domain signal, okay? Inversion can be taken by using integral, or inversion can be taken by using a comparison technique that you know, if we know the Fourier transform of some representative signal. An example is there. For example, say we have a system whose HT and XT are given. You see that your HT and XT both has a sine function, And in time domain, if you want to convolute them, it is not that easy, but we can easily find the Fourier transform of xt and st by using your earlier examples. You can easily find that Fourier transform of your input signal will take this form by using the duality property that we discussed earlier, that your Fourier transform of your input will be this, and it will be a constant function of omega ranging from omega equal to pi to omega equal to minus pi. That means your Fourier transform of xj omega will be equal to this minus pi to pi. And this is your xj omega. Similarly, if you want to find your hj omega equal to something like this, from minus 2 pi to 2 pi with amplitude equal to 1. This amplitude is equal to 1. This is your hj omega. Now, if you want to find the output yj omega equal to what? Yj omega equal to xj omega multiplied by hj omega. Then if we multiply these two figures, what will happen? Resultantly, what we will get? Okay, try to verify it. If we multiply them, then you will get your hj omega, yj omega is exactly equal to xj omega. So if yj omega equal to xj omega, then we know xt is similarly your yt would be equal to xt. Okay, an example is there. Another example is there that if we want to, by using convolution property, how can we find the Fourier inverse of a signal, something like this? You see that this equation is a bit complicated. This equation is a bit complicated in omega, but we can see that this quantity can be expressed as a product of two functions, 2 divided by omega into sine omega multiplied by 2 divided by omega sine omega. So this is a multiplication of two functions in xj omega. The result into what will happen if we know the Fourier inverse of one of these functions, then you can convolute this function in time domain. With that time domain, that will give you the value of your output. This is illustrated here. You try to verify it. If this is your Fourier transform of a function, then it is, you see that this is a sine function. If it is a sine function, the corresponding inverse will be equal to this. If we have this inverse, then what is there? We have a function that has a magnitude equal to 1, extending from minus 1 to 1, magnitude equal to 1. Then we have another function similar type, magnitude equal to 1 with magnitude equal to 1. Then you convolve it. You know how to convolve these two type of function from chapter 2. Then verify the result. Okay, the result will be, see, if two pulses of this magnitude are convolved, they will be generate a triangular pulse, this thing. Now the convolution property of periodic signal, if we have a periodic signal, this is called circular convolution. If we have a periodic signal, your xt and zt both are periodic. If they are periodic, then Fourier transform is not applicable here. Fourier series will be applicable here. If we have a Fourier series there, then xt will give us Fourier constant xk and yt will give us Fourier constant yk. If your xk and yk are available, xk and zk are available, then yk would be equal to t multiplication of xk and zk, where t is the time period of your signal. Okay, a verification is there, you try to verify it. We will be using this equation just to facilitate taking Fourier series constants of some representative functions, so that it will be helpful for us in determining the Fourier constants of two periodic functions when they will be appearing as convolution. That convolution cannot be taken in time domain so easily, but we can take the convolution in Fourier domain easily. An example is there, example 3.36. Try to redo it. But this equation is very simple to be remembered. Okay, this is what that example. You see that your xt and your zt is given. But if we want to convolve our xt with zt in time domain, it is a bit tedious. Then what you can do, we can have our xk determined earlier, the Fourier constant of xk. By inspection, you can find the Fourier constant of zk. Then you multiply your xk with zk, and with the time period equal to 1, that will give you yk. Once your yk is available, then we can again go back to yt by simple using a Fourier series, because you know that your yt would be equal to what? If your yk is available, Fourier constant yk is available, if we have our yk available, if yk is available, then your yt equal to what? Your yt would be equal to sum k equal minus infinity to infinity yk into e to the power j omega 0 kt. This is what your time domain signal yt. Then the technique is what? If two signals are given, then from xt you find your xk, from zt you find zk. Then if t is the time period of this signal, then your yk would be equal to t multiplied by xk into zk. So once your yk is available, you can again reconstruct your signal by using this reconstruction equation of Fourier series. Again, your sum will be finite depending on the magnitude, how the magnitudes are changing with k. Then you can truncate the higher order terms with smaller amplitude. This example is illustrated here. Now we have another two other properties. This is also very important in order to simplify our calculation. One is your differentiation property, another is integral property. Okay, you can easily verify this differentiation property. Of course, the differentiation has there. We have two variables there. One is frequency, another is time. Differentiation can be done both in frequency and time. So these two different, we are dealing with time differentiation at this stage. So we know that the Fourier reconstruction equation is this. This is your Fourier reconstruction equation. Then if we take the Fourier differentiation of this equation with respect to time, that integral is done with respect to omega, then you can easily say that only this vector will be considering for differentiation, and we can easily differentiate it. So this vector will be equal to j omega e to the power j omega t. Then what is happening? This quantity now, another issue, that x j omega is multiplied by j omega. You cannot take this thing out of the integral. So this quantity can be taken as, say, x1 j omega. If this is x1 j omega, then this integral 1 by twice pi from minus infinity to infinity x1 j omega e to the power j omega t d omega. this will be equal to what? This will be a signal, say x1t. That x1t is equal to dx by dt. So in this way, what you can see, say that if we have our xj omega of a signal known, then if we multiply the signal Fourier transform with j omega, then this becomes the Fourier transform of the derivative of xj, xt. In the same way, the integral property can be thought as just dividing your xj omega by j omega, but this will not be applicable for omega equal to 0, but at omega equal to 0, as the thing will become infinity. Okay, so the illustration of this property. If we have a function e to the power at ut, its Fourier transform is 1 divided by a plus j omega, that you know. If we take the derivative of this function, then the corresponding Fourier transform would be equal to j omega multiplied by 1 divided by alpha x plus j omega. In this way, we can verify it. Okay, the verification is given there. You know that this signal, it is very simple thing that this signal e to the power at ut contains a function ut. If we differentiate it by parts, you will see that first term will be equal to ut into differentiation of e ut dt, and second term will be equal to this. In the second case, you have to take the derivative of ut with respect to t. That will give you a delta t. As a result, this will be your total derivative. You can verify it if you take the Fourier transform. Then Fourier transform of your first term equal to this. Fourier transform of second term equal to 1. And simplify it, it will be equal to this. So without going to this derivative, if you know the property, you can directly find the Fourier transform of the derivative of that function. Lots of other properties are there. Huge time will be needed to finish it, but I will be skipping few of them. You try to remember the thing, okay? Some examples are there. You can find this example by using the differentiation property and integration property. You can find the thing is there, okay? Now, another issue is that by using this property, what you can do, we can solve the differential equations also. We know that the input-output relationship in our time domain, continuous time domain, can be represented by differential equation of this form. This is what your input side, output side, this is your input side. Now we know that if we take the derivative once, that will cause a multiplication factor of j omega. If we take the derivative, say, k times, what will happen? That will be equal to j omega to the power k. So in this way, your left-hand side can be transferred into Fourier transform equation, something like this. That means d, if Fourier transform ft of yt equal to, say, yj omega. We do not know yj omega, but we can write it that if the Fourier transform of yt equal to yj omega, then what will be the Fourier transform of y dk dtk yk? This will be equal to j omega to the power k yj omega. This is the Fourier transform of this term. In this way, your left-hand side can be represented in this way, your right-hand side can be represented in this way. Now, which of this quantity will be known to us? Gumaiteso.
Sir, BK and AK.
BK and AK, but BK AK will not help you to solve this equation. You have your input side here, you have your output side here, because your input transform, input xt will be known to you. If your input xt is known to you, then from input you can find your xj omega by taking Fourier transform. But you do not know what is your output in the transform yj omega. So in this equation, you have to solve for yj omega. Okay, so if we find the ratio yj omega by xj omega, what is it? It is not your hj omega, the transfer function.
Yes, sir.
So in this way, you can easily find the transfer function from your input-output relationship. Then you have how many ways to find the transfer function? You have 3 ways to find the transfer function. One, if the impulse response is known to you in time domain, then you take the Fourier transform of ht to get your h omega. This is one. Another thing is that you transfer your system into frequency domain, then you apply your network theorem or laws there. Then you can find the input-output ratio to find your h omega. This is the second one. Third one is if you know the input-output relationship in time domain in the form of differential equation, then we take the Fourier transform of the differential equation by simply replacing the derivative term by j omega. Then we will be obtaining equation of this form. Then you rearrange this equation to find the ratio yj omega by xj omega. That is what you transfer function. Okay. We can illustrate it by using an example. Let me share the whiteboard just to show this thing to you. Okay, consider that we have an RLC circuit, okay? If we have a simple example of a second order system, that if we have the voltage input xt, this is your R, this is your L, this is your C, and you need to find the output across, this is your output, say Y. The output is the voltage across your capacitor. Then if we want to write the input-output relationship, how can we write it? You see that your xt will be equal to Ri, say, plus say this current is I, L di by dt plus Vy. And we know that your I would be equal to C dy by dt. Then your xt would be equal to what? Rc dy by dt plus Lc d2y dt2 plus y. Then if we rearrange the equation into input-output form, you see that it is d2, say Lc d2y dt2 plus Rc dy by dt plus y is equal to x, isn't it?
Yes, sir.
Okay, then can you compare this equation with the general equation that we put? General equation was sum ak into dk dtt yk, isn't it? The output side. Then this is your output side. If we take the Fourier transform of the output side, then what will happen? Your LC, this is your constant ak, into your second derivative was there. You replace the thing by j omega square. Fourier transform of your output is equal to yj omega. This is your first term of Fourier transform. Second term would be equal to Rc j omega into yj omega plus Fourier transform of y is equal to y j omega. That will be equal to Fourier transform of x j omega. Is it not the Fourier transform equation of this time domain equation?
Yes, sir.
Then can you find the ratio yj omega by xj omega? Equal to what? 1 divided by Lc into j omega square plus Rc j omega plus 1, isn't it?
Yes, sir.
So this is what your A says, the transfer function of your RLC circuit. If we take output across the capacitor, your input is a voltage, okay? So in this way, if this equation is available, this is your what? Hj omega. If your Hj omega, if you want to find Ht, what you need to do? You have to take the Fourier inverse of this term, isn't it?
Yes, sir.
Now, how can we take the Fourier inverse of this term? It is very simple, okay? That I will be considering something here in advance, okay? You can skip those parts from your text. So what you can do, Okay, for example, say this is your SS. If your SS, okay, consider that j omega equal to S. Then it is equal to what? 1 divided by what? LCS square plus RCS plus 1, isn't it?
Yes, sir.
Then can't we, for example, factorize it into this form S minus S1 into S minus S2? Can you do that?
Yes, sir.
Then can we put into this form, say A divided by S minus S1 plus B divided by S minus S2? Can you do that?
Yes, sir.
Then your HT equal to what? Your HT equal to A e to the power S1T plus B e to the power S2T, okay? Your S1 can be real, can be complex, conjugate, isn't it? It depends on the value of LCR, isn't it? Depending
Yes,
on the
sir.
value of RLC, the nature of S1 and S2 will be determined. This is a second order system. So in this way, what you can do, you can calculate your output, impulse response. Now the case is that in our case, as you know that we replaced S by j omega. So after having this thing done, you again replace your S by j omega. That will give you your HT by using Fourier transform. In this way, you can go. So you're taking your Fourier inverse and Laplace inverse are nearly same. In this case, in Laplace case, your S is equal to sigma plus j omega. But in the Fourier case, this sigma is set equal to 0, then it becomes your Fourier term. Okay. So in this way, you can also calculate the Fourier inverse. For example, say if your HT, if your Hj omega, has this form 1 divided by say 1 plus j omega plus 2 divided by say 3 plus j omega. In this form, you get after partial fraction. Then your HT would be equal to what? E to the power minus t ut plus e to the power minus 3t ut, isn't it? 2 into.
Sir.
Is it okay?
Yes, sir.
Because you know that e to the power minus at ut, the Fourier transform of the ft of this equation equal to what? 1 divided by a plus j omega, isn't it? So if we compare this thing in this way, then if we are getting this term in your Fourier transform, then you can easily replace that term by the corresponding time domain in the Fourier inverse, isn't it? By simple comparison. So taking Fourier inverse, sometimes you can evaluate it by using integral, but in most of the cases, we do not need integral, okay? We can use a simple comparison technique just to convert our frequency domain signal to time domain one. So in this way, what you can do then, you can, if we know the input-output relationship of our LTI system, then we can apply our Fourier transform directly there to convert the equation into frequency domain. And from that frequency domain equation, you can easily calculate or find the transfer function of your system. Once your transfer function is available, then you take the inverse of transfer function to get the impulse response. An example is there, and similar type of example you have already learned in your control engineering. This is your microelectric system accelerometer example. It is a simple mass, spring and damper model like RLC circuit. The circuit that we have already seen there, in our case, this same equation can be put into the second order form. Is it not a second order equation?
Yes, sir.
So then this transfer function is for a second order system. You can easily analyze the result. If you have a second order system, then we know that the frequency response may contain a resonance point. And you know it from your earlier circuit theory that if we change the value of RL and C at some point, a resonance might occur. At that resonance, you can easily calculate few quantities called bandwidth and quality factor Q. I will not be discussing the thing there because you know the thing from your circuit theory. So try to have a look. Now, if we have a periodic signal, what change will be there in the Fourier constants? Because we talked about Fourier series. Now, if we have our periodic signal, you know that periodic signal will have discrete frequency. That is the integer multiple of k omega 0. But if we want to take the derivative of our input signal, we have seen that in the Fourier transform, we replace the derivative by j omega. Then in our case, what will happen, as this continuous frequency will not be available in the case of Fourier series, here in this case of Fourier series, that continuous frequency will be replaced by this discrete frequency j k omega 0. That means a differentiation of an input signal. If we have this Fourier series, and if you want to take the derivative, you will see that your derivative will be applicable on the factor that contains time. Then that will result you a factor j k omega 0. That is very similar to replacing j omega by j k omega 0. So what in conclusion, what can we say? That if we have a signal xt whose Fourier constant is xk, and our Fourier constants are all referred to exponential form. Then if we have another signal yt, that yt is equal to dx by dt, that means derivative of a signal, that, and the Fourier, this is your Fourier series. The Fourier series of this signal will be equal to j omega 0 k x, Fourier constant will be equal to xk. So you can see that that yk, the Fourier constant of the resulting signal yt, would be equal to just simple multiplication of j omega 0 k with the Fourier constant of original signal xt. Then we will get the signal. Okay, this will help us to determine the Fourier series of some higher order functions. As we know that if we differentiate a higher order function in time, the order will be reduced. As a result, it will be easier. A triangular wave can be converted into a square wave. And you see that for a square wave, it is easier to find the Fourier constant than a triangular wave. So what you can do then, if a triangular wave is given, you differentiate you first. After this differentiation, you will get a simpler waveform and you Fourier analyze it. After that Fourier analysis is made, then you divide that Fourier constant by j omega 0 k. That will be the Fourier series constants of the original signal. The illustration is there. For example, say, and you have to solve it by your own. I am giving some hint only. Look, if we have a signal, their signal is this. And it is a periodic signal, but if we have our axis here, then you see that it appears to be a bit what? For example, in this case, you see that if we want to investigate it, it is periodic signal, but the period starts at not at signal value at this point. Then at this point, it starts at this point. If you want to cover one cycle, you have to come here, isn't it?
Yes, sir.
You understand the point? Okay. Now, if someone will tell you just to find the Fourier series of this equation or of this function, then what you can do? We can differentiate this function. Then if we differentiate it, then you will get a square wave, something like this. Okay, can you prove it, how that square wave will be something like this? Okay, you can see that between time t equal to t by 4 to t by 4, from this point to this point, is it not a straight line?
Yes, sir.
What is the slope of this straight line? If you can easily find this thing, okay, if this is your straight line, what is the slope? Because you can easily calculate what is the time length between these two. Is it not 2 divided by,
T by 2.
It's a T by 2.
yeah, it is t by 2, isn't it? If it is t by 2, then slope of this line equal to what? T divided by t by 2 is equal to 2, isn't it?
Yes, sir.
So then if we differentiate it, what will happen? If we differentiate it, differentiation means what? You are calculating,
So we'll get 2.
you are calculating the slope. So it will be equal to 2, isn't it? And that 2 is ranging from where to where? From minus t by 4 to minus t by 4 to t by 4, isn't it? Again, in this case, from minus t by 4 to this point, what is happening there? Is it not a negative slope?
Yes, sir.
If we have this negative slope and the slope is same, isn't it?
Yes, sir.
So then what will happen? Take the derivative, that will take this form, isn't it? So in this way, we can easily, without deriving anything there that is written in your text, but you can readily find a derivative term, something like this, isn't it? So which wave is easier to Fourier analyze? The triangular one or the square one?
The square one.
Square one. Even you can use the previously obtained result to find the Fourier series of your ZT. The if your ZT is available, then how can we find our YT? For example, YK, your objective was you have been asked to find, for example, the Fourier constant YK. Then what we are obtaining, we are differentiating our
So we have to integrate
dy by dt, then we are obtaining a very simpler signal. Then we can easily find this, we are calling this signal ZT. And we know that Zk, the Fourier transform constant of Zk is very easy to be determined if Zk is available. Then what do you need? By using that Zk, we have to obtain Yk, isn't it? Then we know that for differentiation property, that if we have a differentiated version of our signal, that signal will be in Fourier domain will be equal to j omega k0 into what? J omega k0 into Yk is equal to Zk, isn't it?
Yes, sir.
So which one is known to us?
Zk is known to us.
Zk is known to us. Then we can easily calculate Yk. But when we are calculating Yk would be equal to Z omega 0 k, omega 0 k, not omega k0. Then you see that at k equal to 0, that means if you want to calculate the average value, that cannot be calculated by using this equation. So your y0 constant should be determined separately, isn't it? Otherwise, this equation cannot be used to calculate your y0 can be determined by inspection from your equation, okay, by taking the average value over one period of your signal. And that average value is equal to actually the Fourier constant at k equal to 0 for exponential form of Fourier series. But there is a factor in the case of what? Trigonometric form. But we are not using trigonometric form, so it is very easy to find the Fourier average value by simply replacing k equal to 0 in your equation. If your equation will not yield that value, then you have to calculate it separately by taking the average value of your function within one period. So this illustration is further explained here. Now, another counterpart, okay, differentiation in frequency domain. This is also important in our many applications. Uh, if we have a signal, we are starting with Fourier transform. So if we have a signal whose Fourier transform is this, that means xt is your aperiodic signal. Then if we differentiate it, what is happen in the differentiation frequency domain means you have to operate the differentiation or integration on xj omega. Xj omega is your frequency domain Fourier transform function of xt. If we have our xj omega, if we differentiate our xj omega with respect to omega, because this is the function of omega, then the corresponding equation to the right hand side is this, because your this integral is evaluated in time. So when we are differentiating with respect to omega, this term exponential e to the power j omega t will be considered for differentiation. Then e to the power j minus j omega t d omega is equal to what? It is equal to minus jt e to the power minus j omega t, isn't it? With respect to omega. Differentiation with respect to
Yes.
Omega.
omega. Okay. Then what is happening then? This can be thought, for example, say another function of omega. That if we want to just verify, group it this term, the term that contain t, then you can consider this as yt. So we will find yt a signal that is the complex multiplication of t with xt. And if we take the Fourier transform of yt from minus infinity to infinity to the power j minus j omega t dt, that is equal to minus jt xt e to the power minus j omega t dt from minus infinity to infinity. Is it not the Fourier transform of this quantity is this? So your gd dj omega, the xj omega, we are representing it by yj omega. That yj omega is nothing but the Fourier transform of minus jt xt. In this way, if we have a function that will contain the multiplication of independent variable with use signal, then this property can help us to find the Fourier transform of the resulting signal. The few properties will help you to find the Fourier transform or Fourier inverse in an easier way. That's why these properties are needed. Then we have two other important properties, because I have to finish the properties today. Otherwise, some important topic could not be finished. Okay, this summary is there. Okay, try to remember this table. Some applications are there. You try to, okay, this property is very important that I need to discuss about, okay? The time shifting property. Already we have discussed the thing in our, during our Fourier transform, when we discussed about discrete time Fourier transform, even continuous time Fourier transform, we have discussed the thing. For example, say if we have a delta n, then its Fourier transform is equal to what? Its Fourier transform is equal to 1. But if we have delta n minus n0, what is its Fourier transform? Was not it equal to minus j capital N into n0? This term, can you remember this thing from our last classes? Until class test, this type of problem was also there. Very simple. So if we have our, this is expressed in this property, okay? That if we have a signal xn, discrete time whose Fourier transform is x e to the power j omega, Then if we shift the signal by n0 numbers of samples, it can be to the right or can be to the left, depending on the sign of n0, that will be equal to E j capital omega n0 multiplication by x e to the power j omega 0. That means a shift factor will be multiplied with the Fourier transform. That shift factor is equal to e to the power minus j omega n0. Same thing is applicable for the case of continuous time. That means if we have a signal xt Fourier transform with xj omega, then if we shift the signal, what changes will be there in the Fourier transform? Only a multiplication factor due to that time shift will be there e to the power j omega t0 t. Okay, that is applicable for Fourier series also. Instead of continuous frequency, our frequency will be replaced by k omega 0, because not all frequency will be present for the case of Fourier series. This will help us actually to determine the Fourier. For example, say just for Fourier series, I am showing some example. Okay, consider that we have a signal, something like this, periodic signal. Say this is t by 4 minus t by 4, and this is your t by 2 to t by 2. Just I am showing one period. Okay, this is your time axis at t equal to 0. Okay, we know, for example, the Fourier constant xk of this signal, very easy to be determined. Now, if someone will tell you that we need to shift the signal in this way, so this is 0 to t by 2. What is the, okay, just I am showing only this cycle. I am just, can you compare these two? What is happening there in the second case? What is the relationship between this xt and say this is yt? Is it not your signal shifted by
Yes, sir.
t divided by 4 to the right?
Yes, sir.
That's a yt equal to what? Your yt equal to xt minus t by 4, isn't it?
Yes, sir.
That's so if we know, for example, the Fourier constant xk, then what will be the Fourier constant yk? Your yk would be equal to xk multiplied by e to the power minus j k omega 0 multiplied by t divided by 4, isn't it?
Yes, sir.
So this is very easy to be determined. In either way you can go. Okay, if someone will shift to the left, accordingly this factor should be determined. Okay, this is illustrated here. Okay, you try to look at it. I have already discussed the thing. Now the frequency response for you discrete time case, like you previously discussed what we call continuous time case. If we have the input output relationship for our discrete time case, then you see that in the discrete time case, our input output relationship will be coming in the form of what? Difference equation, isn't it? If we have a difference equation, then how can we transfer it into frequency domain? By using Fourier transform. Just you see that in the difference equation, rather than differential properties, here you see that our time shift property will be applicable. The reason is that in the difference equation, we have our input and output samples that are shifted by certain numbers of sample. Okay, in the case of for example, in the input side we will have this polynomial. At the output side we will have that. Input side we will have that polynomial. At the output side we will have that polynomial. Then you see that if we know the Fourier transform of the input xn is equal to say x e to the power j capital omega, then if we shift x to, for example, k numbers of samples, then what change will be there? it will be equal to e to the power minus k capital J capital omega into x e to the power j capital omega, isn't it? The Fourier transform. The Fourier transform. Okay, so if we have a signal, say z, something like this, the Fourier transform of this signal will be equal to this. Then the output side can easily be written in this way, that if we shift, for example, a signal in this form, then it can be written in this form. You see that e to the power, in this case, like our previously obtained continuous time case, okay, it is exponent by k rather than putting e to the power delta k. Is it not equal to e to the power minus delta omega 0 k, where k is the number of samples in the your difference equation are the same?
Yes, sir.
So in this way, like your continuous time case, you can find the ratio of your output transform y e to the power j omega 0 divided by input transform e to the power a j omega 0. And that will give you a discrete time frequency response of your system. So like your earlier case, if the input output relationship is given, from that input output relationship, you can easily transfer it into frequency domain. Then you can find the input output ratio, that is what your transfer function. Or if your impulse response is given, you take the Fourier transform to find the transfer function. We have illustrated this thing for the case of moving average system in our last class. We will not be discussing much about the discrete time system at this point. So try to remember this. So this is the properties of frequency shift. That means if we have a signal, you see that because this will be needed later in the case the case of sampling of our signal, the frequency shift properties. That means if a shipment is occurring in the frequency domain, what changes will be there in the time domain. Just carefully look at it. It is not very difficult to understand. Okay, this is your signal in the frequency domain. Okay, originally our signal was xt, corresponding Fourier transform was xj omega. Now if we shift, for example, in frequency by an amount equal to gamma is of course the frequency, then the corresponding time domain signal will be equal to this. This type of properties is also there in the case of Laplace transform. Similarly, in the case of Fourier series, the term will be coming as discrete frequencies. And if we have our discrete time signal, here capital tau is used as frequency shift, then corresponding time domain signal will be this for the case of Fourier transform, and this is for the case of Fourier series. So this factor will be appearing as a consequence of that frequency shift. That frequency shift will be associated with a complex multiplication factor in the time domain. And your time shift is occurring effectively as a complex multiplication factor in the frequency domain. That duality property we have to remember. And again, you need not to verify the thing. You simply apply the thing in our practice, okay, when we need it. Okay, consider this, how it will help us to find the Fourier transform due to using frequency shift properties, something like this. Okay, consider we have a signal xt, and that signal is defined in the time domain from minus pi to pi. And another signal is zt is there, another signal xt is there, something like this. Okay, then we can easily find a relationship between xt and zt. Okay, that relationship is equal to this. That means actually this is what? Your xt, is it not a pulse? It is a pulse of unit amplitude from minus pi to pi, isn't it? And
Yes, sir.
this is a signal, this is a complex signal and defined from minus pi to pi. If we multiply that signal zt by xt, then what will happen? Only a complex, okay. For example, if this quantity is appearing as what? As a multiplication factor for your signal xt. So you can easily find that your zt is equal to e to the power j omega t. This is what your original signal multiplied by xt. This can be a complex one or it can be real one, no problem. But if we have this thing with us and want to take the Fourier transform, because you know that Fourier transform of xt is easier to be determined. It is a simple pulse. And we know from our previous example that this is what your Fourier transform. Then this multiplication, if we compare this thing with the multiplication e to the power, say gamma j, gamma t with xt, the corresponding Fourier transform was x j omega minus gamma, isn't it? A frequency shift was there. The correspondingly, here the gamma factor equal to what? Is it not equal to 10?
Yes, sir.
So the corresponding Fourier transform will be equal to what? A frequency shift in the in your frequency domain. Okay. So in this way, actually, if this is known to us, then we know x j omega equal to this. You simply replace your omega by omega minus 10. Then this will be the Fourier transform of zt. But if you want to evaluate it by using classical technique, it will take longer time, not impossible, but longer time to calculate. Okay. So this simple property will help us to find the Fourier transform of some functions that appears to be a bit complicated in the time domain. Using multiplication properties and two consecutive properties are there. Okay, one is your convolution property, another is your what property? For example, if you want to evaluate, someone will tell you just find the Fourier transform of xt. If you want to find the Fourier transform of xt is defined as the derivative of convolution of two functions. Okay.
Yes, sir.
Is it easier? Is it a bit? Isn't it a bit difficult to do in the time domain? Because it is not impossible, but it will take longer time. First, you have to convolute these two functions. After having your convolution obtained, then you take the derivative. Then your time domain function xt will be available. Then once your xt is available, then again you have to apply your Fourier transform equation to transform it. But without going to that rigorous calculation, what you can do, you know the Fourier properties of our signal. Okay. First, you consider this is your yt. So you see that your xt is equal to derivative of yt, isn't it? Then this derivative property says that if your xj omega is equal to what? Xj omega would be equal to j omega multiplied by yj omega, isn't it?
Yes, sir.
Then our problem is then what? Only the thing is that we have to calculate our yj omega. If you want to calculate yj omega, we know that your yt would be equal to convolution of e to the power minus 3t ut with convolution what? E to the power minus t ut minus 2, something like this. Then we have to find the Fourier transform of this convolution. But we know the convolution property that you can consider this at y1t, this is your y2t. This was y1t convolution y2t. Then yj omega would be equal to what? y1j omega multiplied by y2j omega, isn't it? Convolution
Yes,
will
sir.
result in a multiplication in the frequency domain. Then what is, your problem is simplified in this way that you need to find the Fourier transform of yt and y1t and Fourier transform of y2t. We represented y1t equal to e to the power minus t ut and y2t equal to e to the power minus t ut minus t. So this is what your y1t, and this is what your y1 j omega. So your y1 j omega is obtained. Similarly, you have your y2t. You see some changes is needed in y2t. Okay, you see if you want to use this equation there, what you need to do? Okay, you have to write the equation in this way: ut minus 2, ut minus 2. Okay, otherwise time shift operation cannot be applied there. But our function was what? E to the power minus t. What you can do? You can just write minus 2 plus 2. Can we write this? And that will be equal to what? E to the power minus t minus 2 into e to the power minus 2. Okay. That's why that e to the power minus 2 is coming here. And we have this thing. Okay. This is not a function of time. So in taking Fourier transform, this in our notation, this is actually y2 j omega. Then that will be equal to this. And you know the Fourier transform e to the power minus t is equal to 1 divided by 1 plus j omega. Due to that time shift, e to the power minus j2 omega 0, this factor is coming, you know, from the time shift property. So your yj omega and y1 j omega and y2 j omega are known to you. You multiply them together. If you multiply them together, this is what your multiplication. Okay. So then after having this thing done, we have to again go back to time domain, isn't it? How can we go back to time domain? Can you go back to time domain by using comparison? Okay, try to do it. You can easily factorize it into two factors without considering, for example, this thing, because this will be appearing, because this is a multiplication in the frequency domain with a time shift. Resultantly, what will happen? This factor in time domain will cause a delay of time by 2 time unit to the right. So you think is the, for example, say, if we have a function e to the power, say, j omega 2 j omega, you have a function e to the power minus j2 omega, and another function is there 1 plus j omega. If we want to take the Fourier inverse of this function, what will be the Fourier inverse? We need not to consider this factor initially. We can consider the factor 1 plus j omega. The corresponding time domain will be equal to e to the power tut, isn't it? Now
Yes, sir.
this factor is causing what? This factor is causing a time shift equal to 2 time unit, isn't it?
Yes, sir.
So in this way, you can deal with this thing. Okay. First, you do not consider that time delay factor. Then you partial fraction it. After partial fraction, take your Fourier inverse. Once your Fourier inverse is available, then this factor will cause a delay by 2 time unit to the right.
Yes, sir.
So we have almost at the end of our properties. So we are left with the integration property. I will be requesting you to look at the table 3.6 and some examples are there. Hopefully we will be going to application oriented problem in the next class, okay? Because lots of properties are there, not all properties we need at this moment, but application is very important for us. For this region, we will be going to application side. But few example I will illustrate, interesting one. Then another property is called perseverance relationship. I will be giving it to you for self-study, but I will be discussing on it in the next class in detail, okay? Article 3.16, please take note, okay? Then after having this thing done, we will be discussing few things about application. Then we will be switching to our Laplace transform issues. But in the Laplace transform case, as you have already the thing with you in your mathematics as well as in your control engineering, we will be emphasizing on application side only. It is very difficult for me to sit continuously on table for 1.5 hours. I am having back pain. Okay. You are section B?
Yes,
Yes,
sir.
sir.